in order to better understand the mathematics of amplitude modulation, let's look at some basic properties of the Fourier transform. To begin with, consider the product of two time domain functions x1 and x2, and those form the result y of t. Now, if we take the Fourier transform of each of those signals, y, x1, and x2, then multiplication of the two signals becomes convolution in the frequency domain. So we say that multiplication of two time domain signals is the same thing as convolving the Fourier transform of each one of those signals. So we can say that multiplication and convolution constitute a Fourier transform pair. Next, consider what happens when one of these signals is a sinusoid specifically. So say for x1, that's a sinusoid operating at the frequency f sub m, where f sub m stands for the modulating frequency. And I'll multiply that now by x of t. So x of t is multiplied by a sinusoid. Well, the spectrum of that result is the spectrum of x convolved with the Fourier transform of a cosine. All right, so we say that now we're looking at the modulation of x of t by a sinusoid. And the frequency of that sinusoid is f sub m again. Now, what's the Fourier transform of a cosine? It turns out that since cosine has all of its energy concentrated at a specific frequency, fm, then we say that the Fourier transform ends up being a Dirac delta function placed at fm and another one placed at minus fm. So we have a pair of delta functions in the frequency domain. Since the original amplitude was 1, when we divide that in half, then we need to reduce the amplitude by a factor of 2. So the delta function, or delta of f minus fm, is actually the component on the positive side. Delta of f plus fm is the component on the negative side. Let me use some generic shape for x of f, like a triangle. So we would say that the signal has some DC component and it has some finite bandwidth. When we convolve those two signals together, the convolution of a signal with an impulse function simply translates that original function to wherever that delta function is centered. So we're going to translate one replica of our so-called baseband signal to be located at fm. The other replica gets placed at minus fm. And again, if we started out with an original amplitude of 1 on our source signal, then when we split it in half and translate it in either direction, we also have to divide the amplitude by 2. So altogether, we could say that the spectrum associated with a modulated signal will be half of the spectrum shifted to plus fm and half of the spectrum shifted in the opposite direction to minus fm. So when we compare these, or compare the time domain version of y to its frequency domain version of y, we say that this is the modulation property of the Fourier transform.